Test 1, 2, 3. Okay. This is the sixth of our lectures. I realized last lecture we started materials on probability, and it might have come as too much. Or is it too much? Okay, we will spend some time review the last lecture. And then we have given multiple views to linear regression in terms of optimization, in terms of SVD decomposition, in terms of maximum likelihood interpretation or Bayesian interpretation. Today we're going to look at another example where the data are corrupted not with IID noise, okay, a different kind of noise model. Then we're going to end with the case where the data corrupted with a dependent noise, okay? And how does this Bayesian, or how does this probabilistic view of regression help us handle these more complicated cases? In the maximum likelihood estimation, MLE, we assume there's a fixed underlying model. That's the view held by frequentists who do not believe in priors. Okay. So if noise is Gaussian with a fixed but unknown sigma, so assuming there's an underlying model, we just don't know it yet. And given any domain variable x, the ground truth, the underlying function value f of x is fixed. But unfortunately, during our measurements, what we observe is a corrupted version, that is fx plus n. N is the noise. Here we assume the noise is independent and identically distributed. So every time I sample, doesn't matter in which position in the domain, it's always going to be subject to some noise, but the distribution is the same. So the log likelihood, the reason we take a log is there's a fairly large family, exponential family of functions, distribution functions. When you take a log of that probability distribution, the form becomes much simpler. So usually the log, we talk about log likelihood instead of likelihood itself. So this means I have some f is some underlying parameters, okay? And I'm observing my domain. This is a shorthand notation that at x1, when the random variable x1 assumes the value lowercase x1, and xn, the random variable assumes a particular instance xn. Given that I'm sampling these positions, then at these positions I observe y1 equals the random variable y1 equals a particular value y1, all the way yn, the random variable yn equals yn. Okay? These are given, there's nothing you can do about it. This is the value we observed. What is the probability of that? It's a joint probability of multiple observations. If we assume that observations is just some fixed underlying value corrupted with IID noise, then the joint probability of a bunch of variables becomes the product. It will equals given f, the product of these individual so it's the joint probability is a product of individual probabilities. And when you take a log over this product, it becomes sum of the log likelihood. Okay? And we know that this is the Gaussian distribution. So Gaussian distribution is, for the zero mean, it will be like this. So we just substitute this, the probability of yi given xi is yi minus fxi, because the mean is fx. And it's just substitute into this formula. And because there is a minus sign here, when we take the log, instead of maximizing this, we are minimizing the negative of that value. Likewise, when you do the log of this, it becomes a log of 1 over plus log of e. So this term, the 1 over this also is negative. So when you do the mean, it becomes positive, okay? Sorry. So now we have this term. What does that mean actually? This is Gaussian distribution. Gaussian distribution means it's shaped like this, okay? The mean value is fx. If the y happens to be at the mean value, this probability, this term will be 1. That's a peak value of 1. This is just normalizing constant. Every value will be divided by this constant. So this simply means if this yi, the closer it is to this mean value, the closer it is to this, the probability of observing y, given this f, is large. Okay? But in reality, we don't know which f. So you can pick random f, one f, another f. If I have points, if I have points like this, and I give a line like this, for every point, sorry, it's not the TLS. For every point, you have this vertical discrepancy. And this is huge, right? So this says, if this is the underlying model, the fact that I'm observing at this point, xi, this is xi, this is the yi I observed. The fact that I'm observing this, that probability is rather small. So alternatively, if I have this line, then each has a very short deviation from that. So the probability is large. So Frequentis' point of view is f is unknown but fixed. And for every f, I could evaluate the likelihood. I'm going to go for that solution that gives the maximum likelihood. Okay? So here we have this term. It only contains sigma. It has nothing to do with f. So when you minimize over this term over f, this is just a constant. To every f you evaluate, it's the same constant added to the value. So it doesn't really matter, so we can ditch this. And the sigma is also unknown, but it's constant to every f you evaluate. So it boils down to this. And this is our least square regression criterion, the LSE error. So from this perspective, the ordinary least regression is simply maximum likelihood estimation with IID, Gaussian noise. Now next, we come to the Bayesian point of view. So let's review the Bayesian theorem. Bayesian theorem says the probability of B, their event, you can think of, there's A, there's B, okay? This is A and B both happening. It's like this. You can think of each co-occurrence is a particle in that area. A given B, meaning B already happened. So the possibility of B happening is every possible particle in this B, in this shaded area. This, given this is happening, what's the chance of A happening? So this simply says it is the probability A and B, this intersection area is A and B together, both A and B happening. It's the area of this PAB divided by the probability of B happening, okay? This is called conditional probability. If B already happened, under the circumstance that B happened, what's the chance of observing A again? So you need to normalize by PB. And you can think of, if this is a definition, you already have PAB equals PA given B times PB, right? So you can just move this to this side. You have this equation. So by the same token, A and B are completely symmetrical. You can decompose the other way. You can write a PAB as a PB given A, and given A has happened, and then divided by PB. So PA given B or PB given A is conditional probability. PA and B are the probability of observing A or B independent of each other. Okay? These are known as marginal probabilities. The significance of Bayesian theorem, it expresses a degree of belief expressed as a probability of PA. This is marginal. Without any observation, you have a belief how likely A is going to happen. But how is this probability should be rationally changed to PA given B if you observed an evidence B has happened? For example, yesterday we had the first rain of the season. In the wee hours, I heard there's some raining sound of water. So I thought usually Berkeley, rain season starts in the winter time. So I thought it couldn't be raining. So my belief is the chance of raining is 0 or 0.01. That's my belief. But now I observed evidence. I heard a sound of water. Okay? So I'm going to update my probability. It could be raining. It could be some water pipe broken. Someone's, dumping water somewhere, right? So, but the point is, once I heard this, the sound of water, my belief in whether it's raining outside, without going outside and checking, it is actually raining. That belief needs to be modified. Let's say someone comes into the room, carrying an umbrella. Someone else coming from the other entrance, coming with the hairs all wet, right? And these two people, these are uncorrelated, they don't know each other, and it's completely independent evidence. Given these more observations, your estimation, your belief in whether it's raining outside should be dramatically increased, right? But how, without this Bayesian theorem, how do you turn a belief, some fractional number between 0 and 1, how do you update this number in a principled manner? That's the significance of this theorem. Okay? So with that, you can see that if A, this is a posterior, meaning that something after posterior to the event B happened. My belief in A, given that B has already happened, it can be related to the prior, the likelihood. That is, if A is true, what's the chance of observing B? And what's the chance of A happening by itself? This is the prior. Okay? So now, the posterior probability of F given observation, we have these data X and Y. So far, when we do regression, we assume X are domain variables. We have not considered noise in X. We just consider this observation noise in Y, in the target value. So X is always on this side, on the conditional side. Okay? So my belief in what the underlying model should be, F. So in the Bayesian view, F is not a fixed unknown quantity. It's a distribution. It's a random variable with a certain distribution. For example, I think the underlying linear function should have a slope of 0.5 and intercept 1. Okay? That I think it should be, ballpark, it's in that ballpark, meaning that if it's 0.51, intercept 1, it's not as likely, but it's also pretty likely. But if it's 0.1 slope, 0 intercept, that is very unlikely. Okay? Something like that. But the thing is, it has every value is possible. It's just how likely it is. So that's a very different view from MLE, where it assumes it's fixed. That is, every value is possible. It's just one is more likely than the other. So F given Y and X, we just apply this P A given B equals PB given A, PA divided by PB. We just, let A be my F, let B be my Y. I just substitute into this, becomes Y over F. So X, you can see, is always on the conditional side. You can just, for the time being, you can just get rid of this. So it's much simpler. Just PY given F, PF, and divided by P of Y. Now I have PF given X. We get to this point because we assume the prior given X, my belief in F has nothing to do where I sample the data point. My belief in the rain has nothing to do with, of this season, has nothing to do when I make an observation. 5 o'clock, 6 o'clock, it doesn't matter. Okay? So then, when I put I apply log to it, and then this becomes log of this minus log of the denominator. This term has nothing to do with F. It's irrelevant, right? So as far as, I'm using this to score every function. So this is just a constant as with any F I could evaluate. And And this term is to say, I observe X. If the underlying model is F, what's the likelihood of seeing Y? And this has nothing to do with data. That's why it's called a prior term. This is data term. This is really trying to say, given any F, how well does the model fit the observed data? It's data term, data fidelity. How well does it explain the observation? This is my prior belief. So essentially, I can evaluate every point in the model space. I have this score. The Bayesian view is just a distribution in that space. But for practicality, I want to get one model. So I'm go for the MAP solution, maximum posterior estimation. Okay? I mean, if you think about it, if in the end it's a Gaussian, you get this value. I mean, the model next to it is probably almost equally good, right? So, but I just, for practical usage, I just want to get one. And I will go for the optimum. Sometimes when the computation, you can go for the global optimum, but sometimes you can go for near global optimum if you're under a computational budget, okay? So this is the MAP criteria. If you compare with MLE, the only difference is it has this extra term, prior, okay? So under the Gaussian models, we substitute this. So Gaussian model means two things. One is the noise model is Gaussian. Two is my prior belief is also modeled by Gaussian. And my prior, I assume, I only believe it's probably, for the line example, slope is 0.5, intercept is 1. I believe in this is the most likely solution. And my belief, so this, I have F0, I have sigma F squared. I have some estimation of how much deviation there is with respect to the mean. It could be very peaked, so I highly believe in my estimation. And then this is just this Gaussian model substituted to this equation, we get this. And this is actually the noise. So the noise forms a 0 and a sigma square. The prior is sigma F. F is just to denote it's a sigma, different from the noise sigma. So if the noise is very large, this term is going to be heavily weighted in this loss. It means whatever the solution I have, it's going to heavily pull towards minimizing this term, which is, in this case, which is going to pull you towards your prior belief. So if the data is noisy, the Bayesian MAP solution says, please trust the prior more. If there's no noise, and this doesn't exist, and essentially you want to say, please fit the data, whatever the thing that fits the data is your best solution. In particular, when F0 is at the origin, then, in the case of this linear regression, we essentially have this, right? The usual form is W minus W0. But when W0 is 0, 0, 0, it becomes just this. And that's what we know of ridge regression. Okay? When sigma F approaches infinity, you can think of, I have highly peaked Gaussian, meaning I have very strong prejudice. I think it got to be F0. Doesn't matter what the observation is. Alternatively, someone who is very open to to modify the belief based on the observation. Sorry, so this shouldn't be. So this shouldn't be. So this should be a little lower because when it's flat, it goes down, kind of spreads out. So if the flat all the way, the limiting case is just, you know, completely horizontal, right? It has no preference. Any model is possible. That's just schematic view of this. When there's no model preference, essentially map becomes MLE, or alternative is noiseless data. So essentially this term is 0, it becomes MLE. So looking from this perspective, MLE is mapped with a uniform prior or noiseless training data. This rarely happens. So in practice, it's more like looking at MLE as a map with a uniform prior or no prior, right? Uniform prior is no prior. It doesn't help you localize your solution anyway. Another thing is when you have more and more data, the prior becomes less important because this is just one term. While this term, there are more and more terms to be accumulated. In the end, the prior is not going to matter. Okay. So this is I try to come up with a schematic view about the relationship between map, MLE. MLE is a special case of map when there's no prior or uniform prior. Okay, so the light green is the let's say if this is all the map formulation you could have, MLE is just a special case where the prior is uniform. And this is stripe, this shaded stripe is under the condition that the noise prior assumes Gaussian models. So if it's Gaussian, within MLE, if it's Gaussian, they're reduced to ordinary least square regression. Outside MLE, if both are Gaussian, it becomes ridge regression. I visualize with them touching because when lambda approaches 0, it becomes OLS if it's well conditioned. Okay? So, okay. Any questions? Does it help? Question, yeah. Prior. So what it means to prior. So I say for this season, let's take this rain example. We had a first rain yesterday. Usually it doesn't rain in this season, okay? My prior, without observing anything, is say 0.9%, it shouldn't rain. 0.1% is rain, that's prior. But this is my belief without looking at anything. If you ask me, you know, I'm inside the door, I'm inside the room, I'm not taking any evidence. I close my eyes, you just ask me, I will say that, right? That's my belief, it's prior. The observation here is say, I heard something, or I saw something. I saw through the window, there are raindrops on the window. That's evidence, right? Given that the observations have happened, and I'm gonna update my belief in whether it's raining today or not. So if I see raindrops on my windows, I'm gonna modify it to 0.8, right? Sorry, that's right, 0.8 is not raining, 0.2 is raining, yeah. If I go outside and see it is raining, the rain probability is 1, right? Okay? Does it help? Okay. Okay. We also talk about, you know, in terms of model selection, we talk about, you know, the most important lesson you learn, practical and an important concept is cross-validation, right? But let's look at it from a theoretical point of view. How can we quantify, what it means for the model to underfit or overfit? Right? You need to have some guidance. Okay. So the way we approach this problem is to say, I have a recipe to estimate something. Okay, and I have a task which involves X and Y. But every time I collect my X and Y, it's just one snapshot of this possible data set. So if I go to the field and collect my X and Y, I apply my recipe, I will get best solution. I go to the field the next day, I will observe a new set of data, but I assume they actually come from the same domain, same problem, they come from same distribution. Okay, so what's illustrated here, I have few points. Each plot, you can see that the black points, they are kind of changing the position here and there. But they sort of this the gray line is showing the ground truth. I synthesize the data. I have the ground truth line, I add some noise to it. So every plot, I have new noise, IID noise add to it. But from the data collected from one visit, I get one line. In this case, it's polynomial order of 0, meaning just horizontal line, right? It's not a slope line, it's just a horizontal line, just DC component. So you can see that when the data set changes, my fitted line moves up and down. Okay? Same data, if I choose polynomial order 1, I'm fitting with a slanted line with a certain intercept, move up and down. Okay? And you can see that it starts to fit the red fitted line from least square regression. Now conforms much better with the gray underlying ground truth. The underlying model is P equals 1. And I assume P equals 1. It fits fairly well. But what if, because I don't know that, let's assume P equals 2. Then you can see that, I have those curves that sometimes open up, some open down, right? Okay. Likewise, if I go for the P equals 3, it becomes more curvy. And then you can see the variation across different data sets seem to have more. So this is P equals 0, 0, P equals 1, P equals 2, P equals 3. The previous 4 slides, I dump all the lines fitted, all the data observed in one plot. All the black dots, they are the same. My fitted model from a subset of these black points are illustrated with the red lines or red curves, okay? Now our model assessment is trying to say, can I study this bundle of this line? How do I characterize the difference between these sets of line bundles? What's the principal way to differentiate? Should I go for P equals 0 model, P equals 1 model, P equals 2 model, or P equals 3 model? By studying the behavior, there's line bundles. So you can already see that P equals 1, it's pretty much aligned. There's some fluctuation in the intercept. But when you get to P equals 2, especially at the two ends, it starts to diverge much more, right? And when P gets to 3, even the middle section becomes much bulkier, spreads out a whole lot more. Another thing to look at is to say, on average, does the average model of these model estimated from subsets? When we do cross-validation, we use subsets, yes? Okay? The average model from these subsets estimated model, does the average conform to the ground truth? For example, the average for this P equals 0 will be somewhere like this. For this one will be something like that, right? So this fit the ground truth much better, and this doesn't, even the average model doesn't fit well. So that is bias. You can see this is called a bias. The average model, the deviation of the mean model, average model. So you marginalize the variation in the data set. The mean model is still far from the ground truth. That means you have large bias. Your function family is under the capacity. The capacity is not large enough to entail this underlying model. And this fits well. The bias is 0. Okay? In the p equals 2 and 3, p equals 2, of course, include models p equals 1. The problem is the mean, the mean is sort of like this. But the variance is too large. Meaning whatever training data I have, estimated model, next day I apply to new data, the chance of this predicting well on the new data is very poor. Okay? So if you want a good generalization, you want a small variance. If you wanted to fit the data well, capture the data variation well, you want a bias to small, even on a training set. If you want a good performance to persist to the test set, you want the variance of this good estimator to be small. That's the intuition. So in terms of math, you have, this is the key equation, just by definition. A squared variable, the expectation of this is the variance of this times the expectation squared. That's just one value squared. So our idea of this prediction error, you have a prediction made based on for x at any domain variable x, d is a random variable in this case, it's the data set. So this expectation is taken over d, taken over the random variable y, because y also has observation noise. There are two factors of randomness in this. So you just expand this quadratic term, so it becomes this nothing, it's just straightforward expansion. And for this term, it's some variable squared expectation. Likewise for this, you just apply this equation. You apply to this term, you get this. You apply this equation to this term, you get these two terms. And this h and y are independent of each other because the noise is IID. So the expectation of two independent variables, the product of two variables becomes the product of their expectations. Okay? And then all the color, the cyan, the color terms, you can just complete the squares. You collect them and it gives you this equation. And this just carries over and this carries over. And this is defined as this, look at this, what is this? This is expectation of h of this. So it is the average model. When I vary d, every data set has a h. Through all the data sets, I have an average model. This how much deviation is the average model away from the underlying model? That's called a bias, and I'm taking the square of it. And this one says the variance of that. So the variance is defined by the deviation with respect to the mean. Okay? And this is just the variance of y. And it's just the amount of noise. So this is called irreducible error, because there's nothing you can do. It's the noise model, the corruption added to the observation. So the bias control how accurate, on average, your recipe will give you. The variance, if the variance is small, use this subset or that subset gives you more or less the same performance. So that means, you train with one data set, second day with a new data set. Your previous solution is as good as almost as good as the best solution for the second day's data set, that means your generalization is good, right? The test accuracy will be high. So you want this stability. The noise controls the precision in your measurements in Y. So this shows for this p equals 1. I calculate this. I just run many times because this I can synthesize the data. I run these 200 times, subsets of data. So I can estimate this was my sample average. The whole thing can be decomposed by these three curves. Noise everywhere is same variance. The mean value, the bias is all 0 at p equals 1, the right order. And the variance, you can already see from this curve, you can see it kind of goes two ends, it rises up a little. So you can see it takes this form, okay? So this whole thing, the prediction error, this term is these three curves added together. So it will be something like this, 4. So this is this curve. This curve equals this black curve plus this curve plus this cyan curve. That's the decomposition. There's inherent amount of noise. There's how good the mean estimate approaches the ground truth, and how much variance from individual estimates with respect to the mean. From this perspective, underfitting, meaning you have very large bias, right? You know, just in case of this one, right? Very large bias, there's nothing you can do about it. If this happens, you should try to increase the complexity of your function family. Most overfitting, how is overfitting defined? Small training error, large test error, right? That means your recipe has too much variance. Training error reflects bias because it doesn't involve another data set, right? Any new data set, but not variance. Test error reflects both. If your model is poor, the test error will be large. If the test data is very different from training data, due to the variation, your test error will also be large. Low training error can fool you when you've overfitted. So don't just focus on training error. Of course, you want to optimize it. You try to minimize it. But if if the variance is large, you're not going to get good performance at the test time, and that is what matters. Okay. So when we talk about feature engineering, right? We talk about we can expand the raw data by polynomial features or any nonlinear features. If you add a good feature, essentially you expand the model, the function family to include the underlying function. So you potentially could model it. The question is, if you have enough observations, you can find this optimal solution in the right way. But if your function family if it's outside your function family is this, but the underlying model is here, then you always have bias. If it's in the family, and that has additional factor of whether you have the sufficient number of points, but at least it enables you to locate f if you increase the function family to enlarge this by adding a feature to it, you will be able to locate this, to find this underlying model. But the thing is, adding a feature comes with a cost. It also increases variance. Okay? So you want to add a feature, don't add a feature unless it reduces bias more. There's a trade-off. And how do you decide that? How do you decide whether you should add that feature or not? In practice, how do you decide you should add one feature or not? All this, only for the real world data, we never know F. We can't really calculate bias or variance because Fx is not known to us. So how do we figure out whether we should add a feature or not? Yes, I've been waiting for this answer, cross-validation, right? I'm telling you, the cross-validation is the most important lesson of this whole machine learning class. If you don't remember a thing, just remember cross-validation. The last to go, okay? That's actually practical. Okay, now, we can calculate bias and variance, but it helps us to look at, if we understand it's underfitting, what do we do, right? We should expand the model family. If it's overfitting, we should think about ways to, regularization. We should, it's just give you a very theoretical guidance on how to tweak your model. And sometimes we can test this algorithm on synthetic data. Nowadays, a lot of problems have synthetic data available, right? So for synthetic data, you synthesize everything, you know everything. So there you can evaluate the bias and variance. That would be very helpful for you to understand the algorithm.
So the whole point of taking the expectation of x squared was to figure out the bias and the variance?
The decompose these two aspects, whether the function family is sufficient or, that's a the bias, okay? The variance is to tell you how much generalization there is. Small variance, good generalization. Large variance, very poor generalization. So this all have their counterparts in our cross-validation recipe, okay? So this just shows this decomposition. Everything, all the prediction error, this you have this model bias, they are different from this discrepancy. This shows that, compared to the mean model, you have this much variation. And this is the clearest. Initially, you have line bundles like this. The mean is aligned with the ground truth. And the variance of this just saying that every line, subtract the mean line. So the slanted line becomes horizontal line bundle. So how much, you can see the variation is smaller here, larger here. You can see that, looks quite surprising. All this variation, in the end, they cancel out in the mean model. In theory, we know that because p equals 2 includes p equals 1, right? It's a richer family, so the bias should be 0. But the problem is the variance, you can see the variance compared to this, right, is much greater. And you go to even higher order, the variance is just, the envelope of this is much bigger. And this is putting them together. You can see that p equals 0 is this curve. P equals 1, 2, 3, they're all about 0. They're all together. But the variance really shoots up, going from, the thickness indicate the order. The variance really shoots up. So among these three, which correspond to these three curves, I'm go for p equals 0.1 because that's had the lowest variance. That's consistent with what you get from cross-validation as well. So this curve is with this horizontal axis is my x, right? This prediction error is per x. And this bar plot is actually summing over so it's calculating the area. So for example, this curve, I sum up all the values here. That gives me a bar, okay? Overall, I have this much variance. I have this much bias. This noise is always the same. And you can see that the bias goes down, okay? This goes up has something to do with, you know, you only have few data points. When you have higher order, it becomes much noisier. Your estimation becomes much noisier, okay? Not as reliable, so that's why. So it's from my empirical estimation, there's a noise associated with the small sample size. And you can, the variance, look at the red bars, it goes up, shoots up pretty big. And this unit is taking the square root of the error. So it's actually much bigger than you might think. So in the end, I settled for this p equals 1. So that's another way of looking at it. So I also want to show an example. I mean, this is in a way, the function family includes the point. Oh, you have a question?
Yeah, I just mentioned it, I missed it. Why does the bias go up as you increase?
Oh, here, you mean this one?
Yeah.
In theory, it should go down. But as you increase order, let's say a line, 2 points determine a line. The more points, noisy points you have, you over-determine the system, you can estimate more reliably, right? If a high order model, say 9th order, you need 5 points, it's not gonna help you, you know. You need a whole lot more data set to estimate the optimal solution reliably. And this is a rather small data set, only have like 10 points or something. So the higher order you go, there's a noise, intrinsic noise coming with estimate that quantity. If I only collect the 200 subsets, if I calculate 1,000 or million samples, this just go down, okay? This is, I actually do the numerical experiments to calculate these values, but theoretically, it should go down. Okay. Okay.
Is it P2 subset of P3 though? So
that's right.
if the bias is smaller in P2, then wouldn't the same function be the best model for P3?
That's right. So that's the point I'm making. If you look at the previous, just think about this. The thing is, there's a noise, right? For example, this one, this fits, I get the ground truth line almost perfectly. But if I look for the optimal solution in that family, it becomes this line, right? Because there is noise in the data. So the noise in the training influences your bias. That's one of the points listed, right? So I want to show an example. The underlying model is sinusoidal wave. But my function family is just polynomial functions. And again, only 10 points. Here I have 48 random sets, very small. And you can see that it sort of, fits pretty well. And what I like you take this view. Because I'm fitting in a polynomial function, it's a linear function space, I have slope and intercept. So each of the line I fit, it becomes a point in this space, right? Every circle is my model, is my model from a subset. So the gray point is my underlying model, because the data is generated with a line slope plus some sinusoidal wave deviation. That gray line, gray slope, is at this point. The cyan circle is the average of these model, all these red circles. You can see this fits this pretty well. The overall trend zero bias, although it never captures the undulation.
So why do you want to add a sine wave to the line?
Oh, I want to show the true underlying model is some linear function of this, which within the family, plus something that is highly nonlinear. I just want to show, so in a way, if you only capture this component, you won't be able to fit this component ever. Okay? So, but this gives you a sense, the difference between the cyan circle and the gray point is my bias. Yes? And how far the red points spread out in the space is my variance. Yes? This is another way of looking at this. Instead of looking in the primal space, it's just line bundles. In the model space, just scattered points. Yeah? And so decomposition chart is this. You can see now at every point, X, these points you get a zero bias, but there are a lot of these you cannot model. So if you were able to plot such a curve, you know that your function family is not rich enough to capture the little wiggles. Okay? And this is just showing the variance, just another view of this. And this to show what if I have 100 points instead of 10 points? You see, the variance is much smaller. It's much more condensed. Okay? And this shows the curve. You can see again, you can see the bias. And the variance is significantly reduced. Okay, that's what the curve's like. Bias curve, variance curve, and noise. And just compared to that, you can see going from this, the variance isn't significantly reduced, but the variance, if you focus on the red curve, right, changes reduce significantly. Okay. So we are pro on this topic now, right? Any remaining confusion? Yes?
Can we reduce the bias and variance at the same time by using a more complicated model and get more data?
Yes, very good conjecture. Can we reduce bias and variance by increasing the complexity of the function family, at the same time increase the data? When you increase the complexity of the function family, you can reduce the bias. When you increase the number of points, you reduce the variance. So it's an affirmative yes. Yes.
Can we have the polynomial to be degree 1 and just put it with a straight line and then have the second one to be a Fourier transform of discrete signals so we can actually have a sinusoidal wave going on top of that to actually capture the behavior of the model?
Very good. So he was suggesting for the last sinusoidal wave, can we first fit the line? And then we fit the residual model. We have some model, we have some y. And we already have some f hat, it's from the line family. Instead of trying to fit x and going for y, I'm gonna fit x, go to f hat of x, right? And for that, I'm gonna use sinusoidal function family. This kind of learning is onion peeling, right? You fix some component, you peel it off and fix it with another family. That's a very good idea. The residual, in deep learning, the residual learning takes that idea because the residual usually are much easier to fit. And also related concept is coarse to fine learning in many different areas. If you want to fix a complicated curve, first you have this simple thing, and then you can fix some slow variation, and then you come more high frequency variation. Okay, so this helps to reduce complexity, and each step it's like a cascade of models. Each step, focus on a different aspect. Okay. So now I want to introduce this new concept of weighted least squares. Earlier, all the noise are constant across different observations, the IID. In this case, the instances are not created equal. Xi, Yi, each is weighted by scale Si, okay? Some value. Basically, I value this instance more than others. I know that this point contains less noise. I may take a measurement with a high precision device. Some others may be very coarse precision. Or I know this is very carefully collected data. So I want to give different significance to different instances. Okay? And usually weighted least square, people like to use weight, but since we use W for the model, so I just use scale, which is actually quite proper. So now we have the data matrix. Each X is in the row, the Y is in the row, and the S is just diagonal matrix. This is n by n diagonal matrix. Okay. So this is like a very intuitive starting point to modify the original ordinary least square regression. Earlier we just have this, and every point is considered, each considered the same contributed loss in equal fashion. But now I'm going to give it weights to every loss. If this weight, for instance, I is large, that means the error, the prediction error on this particular instance is considered more heavily in optimizing this criteria. So the consequence of that, you really want to reduce this prediction error on the heavily weighted points because they bring down the total loss much more quickly. Okay? So now if you write it out, this we know is xw minus y. And this thing is n by 1 vector, yes? Yes? Each row is just a prediction error. Each row is just x transpose minus yi. So on and so forth. This is x1, this is xn. Okay? Now I just need to give each row a weight Si. And that's what we do with diagonal matrix, right? When you multiply a matrix, left multiply a matrix with diagonal matrix, you just scale the individual rows. Yes? So essentially this S left multiply this prediction error captures this weighted least square criterion. Now if you look at this, it said, it seems I can turn this into something I know. I multiply S with inside this bracket, I have Sxw minus Sy. So that means instead of doing the weighted least square with x1, y1, s1, each has a weight, I can treat it as, each data instance x1, y1, the data points to be scaled accordingly. Some scaled by 1, some scaled by 2. In the original X or Y space, it doesn't make sense anymore. But for the sake of least square weighted least square fitting, it makes perfect sense. It's equivalent to solve the least square problem on the scaled data. That's just by math. Yes? Okay. So weighted least square is equivalent to least square with scaled data. The scaled data Sx, Sy. Simple. That's from optimization point of view. Since we have this a probabilistic view of least square, so how do we reach this understanding from a probabilistic point of view? So let's just quickly review what we have for MLE for least square. In least square, we assume Gaussian IID noise, and then we derive this function, right? Now, since in the weighted least square, we need to model some data noisier than others. So instead of least square, you have this IID noise on every data point. I'm going to assume each has its own noise level, right? Because some are noisier than others. Noisier data actually weigh less. If I know them to be less noise, I want to weigh them more, right? So essentially the noise model is modified. At this point, they're still independent. They are just no longer identically distributed, but they are independent of each other. But this is just it's now a normal distribution with a variance sigma I squared. That's equivalent to scaling a union norm vector, random variable with sigma I. It's unknown, but it's fixed. It's equivalent, okay? So since we have this equation, since sigma I is just a constant, it's unknown, but it's constant. So if we divide both sides by sigma I have yi divided sigma I, fxi divided by sigma I plus n. This n is union norm distribution. So again, we have IID noise, right? So this is the perspective. Weighted least square is simply least square with a scaled data, right? It becomes each data point divided by the noise level of each point. This, earlier we get to this from optimization point of view, yeah? Or optimizing this loss. This is a view based on modifying the noise model. This is a probabilistic view. They reach the same conclusion. In fact, I don't have to go this route, making connection to least square. I can just go for MLE directly. If I assume the noise is independent, but each has its own individual noise level, so then yi, because in MLE, this assumes fixed but unknown, it makes the observation takes a mean value at this point, and with the noise level, this noise variance as the variance of the target value. And then this is, we just, the joint probability turn into sum of log likelihood of individual instances, because independence assumption, this requires independence. This still holds, this check, right? It's just, they're independent but not identically distributed. Now, because I know this forms this distribution with sigma I just substitute the Gaussian distribution with sigma I as the, in this equation. See, now this one actually has a varying sigmas, but whatever that is, it has nothing to do with F. It's some unknown constant summed over together. So I can just totally ignore that in optimization. So it boils down to this. Okay, this is the second view of deriving weighted least square. You can see weighted least square is MLE with independent individual Gaussian noises. And from this previous, the scale versus the sigma I, essentially the scale is the inverse of the noise level. Noisy data, smaller weights. We have 8 minutes. Should we continue or should we field some questions? Questions? Or no questions? Oh, there are questions.
So the correlation, it seems kind of a little bit too good to be true. Like, what are some issues that we can run into?
The question was, the cross-validation seems too good to be true. What are the problems that we will run into? The key idea of cross-validation is to say, during training, you try to fit the data with certain function families, and approaching this goal allows you to solve the best model. And when you have the validations, you reserve validation so you can pick the hyperparameter, but these two aspects combined together help you to pick the best model that fit the training data. But when you have, you know, the cross-validation to say, when you have different, when you want to use the data most effectively, when you need to compare one model from one approach, another model from a different approach, each require different beliefs, right? You know, different religions, it's very difficult to convince the other camp what you're doing. What's the only acid test you could have? And that is the test accuracy. It's the validation error. It's the ability to generalize. It's the out of sample error. So in a way, it's kind of, you know, when you do the training, you have optimality criteria. That optimality criteria results from how you formulate the model. In this case, the least square regression. Later on, we will learn other kind of criteria. I don't have, you know, here we are still fumbling, wallowing in this least square regression model, even with the nonlinear function family, feature engineering. But there are other kinds of models available. But how do you compare apples with oranges? So you actually have a different criteria. That is just out of sample error. It's just, you know, if you can come up with something that's more general, if it's not about out of sample error, something else that can be shared across these approaches, go for it. I think the cross-validation in a way is just a way of looking at it. You know, you have a modular's approach. You can formulate your epsilon. But in the end, you have this acid test, which is irrespective of how you formulate the model, come up with a solution. It's something that approach, you know, it's born out of the need, and this is the only thing people can think of. It's not too good to be true. It's the only valid solution you could have, because the test out of sample generalization error is common. I don't care how you get a solution. You may just give me a random solution that you submit this random solution, that's my best solution. Even that, I can evaluate. I don't make any assumption. And because of that, I can compare apples with oranges. Yes?
You mentioned earlier that you train your model using synthetic data.
Yeah.
And I was wondering what are some examples, when is it appropriate to use synthetic data and how people might generate it?
For example, one thing I look at this, so I have a question. I pose this question to you. So, you see, this is a line fitting these points, right? In a way, every point contributing, estimating these regressions. Remember this polynomial regression is all about, you have basis curves, you find a few linear combination coefficients, and every point is involved. So why is that the middle section tend to have a smaller variance? Points at the two ends have a larger variance. That's my question to you. How would you understand this? Who would like to venture a conjecture? Why is that? How would you study this by yourself?
Intuitively, interpolating is easier than extrapolating areas farther to have observations from.
Very reasonable assumption, observation. But I will ask you something else. Remember last time we also talked about RBF, radial basis function. So what if I use radial basis function as my nonlinear feature? I applied linear regression to radial basis function. Will I observe the same pattern? I mean, it's very tantalizing to say that, this sort of is going to the, as if there's a coverage of data. And this is more at the edge of coverage, so I'm facing more extrapolation problem. And the middle is more like, you have all the points surrounding you, so more interpolation problem. But is that the reason? So how would you study this? So what I would investigate is to say, I have a different conjecture to be tested out, and I actually would like you guys to do it. I think one of the difference, if you look at the polynomial function family, do I have it maybe here? You see, these bases, these basis functions tend to agree with each other more in the middle section. It really diverges at the further end. That's one hypothesis. RBS have totally different behaviors, each just a bump. It's very well defined range-wise. So if I use RBF as basis, I will do polynomial regression. To do this linear regression over RBF basis, I can use synthetic data to evaluate that. It will help me understand, right, whether this variance behavior, whether it's uniform across the span of the data. So that's an example of using synthetic data to understand the different approaches. Very good. See you next time. Good night.